Okay, good morning. So today's topic is the continuation for previous topic of shear force and bending moment diagrams for simply supported beams. So we have dealt some examples in the last session. So we'll be continuing with some more examples. This example we have seen. Let us see now the example of simply supported beam subjected to a point load, uniformly distributed load, and a couple. So here the procedure is same. The first step is to calculate the reactions RA and RB. Okay, for which we take moments about A, sigma MA equal to 0, which gives RB. So RB into the moment of it, RB into the moment of it about A, the distance of it from A, that is 10 meters. RB into 10 is equal to 20 into 2 plus 30 into 5 into 7.5 minus 40. Minus 40 is the couple which is acting anticlockwise. Which is acting anticlockwise. So the reaction now at B is obtained as 112.5 kilonewtons, and reaction at A is 20 plus 20 plus 150. 150 is total UDL minus RB. So 170 minus 112.5, which is 57.5 kilonewtons. RA is 57.5 kilonewtons. Okay. Now once you find the reactions at A and B, supports A and B. Now the next step is considering different sections. Wherever the load changes, you need to consider a separate section. So here we need to consider sections in portion AC, CD and DB. Separate sections we have to consider between AC, CD and DB. For this section between AC, we can take origin at A, and for this section also between CD, let us take origin at A only, and for the section between DB, let us take the origin at B. So the limits for X for the section between AC are 0 to 2, and the limits for X between C and D are 2 to 5, and the limits of X for the section between B and D are 0 to 5. 0 to 5. Okay. So now consider section between AC. The shear force at X. Consider the section between AC with the limits for X 0 to 2. The shear force at X will be RA, that is okay, RA. It is positive only. Left side upwards is positive as per our convention. So it is 57.5 kilonewtons. And you can see here it is independent of the distance of section. So shear force remains constant between A and B. A and B. A and C. So shear force at A is equal to shear force at C is equal to plus 57.5 kilonewtons. Okay, and at C we have downward load of 20 kilonewtons. So wherever the point load is acting, we find the shear force just to the left of it and just to the right of it. So this shear force at C is just to the left of C. So when you consider the section just to the left, the point load 20 kilonewtons does not come into picture. Okay, and considering just to the right, shear force at C just to the right of C, the shear force will be 57.5 minus 20, that is 37.5 kilonewtons. Okay, so the point load is acting at C, hence there will be a sudden drop or rise in the value of shear force at that point. Okay, so now the bending moment at X, say section between AC, bending moment at X is RA into X, 57.5 X. Okay, so now bending moment at A, that is at X equal to 0, is 0, and bending moment at C is 57.5 into 2, that is at X equal to 2. So this value is 115 kilonewton meters. 115 kilonewton. Okay. Now consider section between CD. Consider section between CD. So shear force at X will be 57.5 positive minus 20, that is 37.5. So X is equal to 0 to 2 to 5. The limits for X are 2 to 5. So if you observe this, it is also independent of distance of section. So shear force remains constant from C to D. Okay. So this shear force at C, which is 37.5, is when we consider the section just to the right. Okay. When you consider the section just to the right of it, the shear force at C is 37.5. Okay. Next, shear force at D is also same, 37.5. It remains constant because there is no load acting between C and D. Okay. Next, bending moment at X between section between CD. Bending moment at X, considering left hand side, is RA, that is 57.5 into X minus 20 into X minus 2. 20 into X minus 2. So the limits for X are 2 to 5. So at X equal to 2, the section will be at C. That is, bending moment at C will be 115 minus 0. This term becomes 0 at X equal to 2. So it is 115 kilonewton meter. Units are kilonewton meters. Next, when X equal to 5, the section will be at D, and the bending moment at D will be 57.5 into 5 minus 20 into 5 minus 2. So this comes out to be 180, 227.5 kilonewton meters. Okay. 227.5 kilonewton meters. Next, we consider the section. If you observe the problem, in the problem, there is a couple acting at D. There is a couple anti-clockwise couple of 40 kilonewton meter is acting at D. Okay, 40 kilonewton meter, and the load is 30 kilonewton per meter. UDL is 30 kilonewton per meter. So again, when there is a couple acting at any point, you need to consider the sections just to the left and just to the right. Okay. So when you consider the section just to the left, the bending moment will be 227.5 kilonewtons, and bending moment at D, considering the section just to the right, you will have the bending moment 227.5, which is already calculated due to the loads, reaction and point load. These are this is clockwise, this is anti-clockwise, and you have anti-clockwise couple. When you consider the section just to the right of D, this 40 kilonewton meter couple comes into picture, so which is anti-clockwise, so that is deducted. So the moment at D just to the right of section D is 187.5 kilonewton meter. Okay, so what you need to observe is there will be a drop of 40 kilonewton meter, sudden drop in the bending moment at D by 40 kilonewton meter, which is the couple acting. Okay, as there is a drop in shear force value when the point load is acting at the point where the point load is acting, there will be a drop in the value of bending moment, sudden drop in the value of bending moment at the point where the couple is acting, Okay. Yeah. Next, consider the section between B and D. Consider the section between B and D. Now for this we will be taking origin at B. Origin at B. So bending shear force at this section X, for the section between BD, the limits for X are 0 to 5. The limits for X are 0 to 5. So the shear force at the section X is VB, that is 112.5x minus moment due to UDL of length X to the right of section. So which is W x square by 2. So it comes out to be 112.5x minus 15x square. 15x square. Oh, sorry. This is bending moment. Coming to shear force, this is bending moment action. Coming to shear force, we have reaction upwards, reaction of 112.5 acting upwards. So right side upwards is negative. As per our convention, left down and right up are negative, and left up and right down are positive. Here the force is upwards and acting on the right side, so it is negative, minus the UDL for a length of x, total UDL for a length of x. This is positive. Right side downwards is positive. Okay. So if you observe this, shear force depends now on distance x. So what does this mean is shear force varies linearly between B and D over the length of 5 meters. And in the portion where UDL is acting, shear force varies linearly. Okay? There is no variation of shear force when there is no load. Shear force remains constant. We have seen the example between AC and CD. In portion BD, there is UDL acting. So the shear force varies linearly. This is the equation for shear force. Okay, it depends on x now. So at x0, at x equal to 0, shear force at B will be, this term becomes 0, it is minus 112.5 kilonewtons. Similarly, at x equal to 5 meters, the limits are 5, okay, 0 to 5. Shear force at D will be minus 112.5 plus 30 into 5. 30 into 5. So it becomes plus 37.5 kilonewtons. So if you observe here, at B it is negative, at D it is positive. So the shear force changes sign at some point between B and D. Between B and D. So it means at that point, the bending moment will be maximum. The point where the shear force changes sign is the point of maximum bending moment. Okay. So to find the location where the shear force becomes 0 is equating this to 0. So by equating this to 0, you will have x value as 112.5 by 30. 112.5 by 30. So it comes out to be 3 point, it comes out to be 3.75 meters. 3.75 meters. Okay. So at this distance from B, the bending moment will be maximum. Okay. And how about the bending moment now? Bending moment at X for this section. Now it is minus 112 plus 112.5 into X, that is sagging, minus 30 into X by 2, that is 30x squared by 2. So it is 15x squared. Okay. So at x equal to 0, bending moment at B will be 0. At x equal to 0, the section will be at B, and from this equation, the bending moment will be 0 at that point. At simple support, actually bending moment is 0. Okay. Now at x equal to 5, the section is at D. So bending moment at D is 112.5 into 5 minus 15 into 5 square. So it comes out to be 207. Not 207. It is 187.5. 187.5 kilonewton. Okay. So considering left side of the section, we have seen, considering right side of the section actually, we get the bending moment at D as 187.5. Considering left side, we are getting it as 227.5. There is a drop of bending moment by 40 units. The 227.5 minus 187.5. There is a drop in the value of bending moment by 40 kilonewton meter. That is due to the couple acting at that point. That's what we have seen. Okay, it is clear. So left side consideration, you are getting 227, and when you consider right hand side, you are getting 187. There is a drop in the value due to the couple. Okay, yeah. How about maximum bending moment at x equal to 3.7? So substituting this value of 3.75 here, 112.5 into 3.75 minus 15 into 3.75 square. So it comes out to be 210.95 kilonewton meters. So this is the maximum bending moment which occurs at a distance of 3.75 meters from B. From B. Okay. Now we can plot the bending moment diagram. We can plot the bending moment diagram. So we have already calculated the values of shear force and bending moment at various points. Okay. Let us first draw the shear force diagram. Okay. So at A, the shear force is 57.5. We have calculated the shear force values. Just you can start plotting those values. Okay. At different distances from A and A. So at A, the shear force is 57.5, and at C, it is same 57.5, remains constant, and there will be a drop in the value of shear force by 20 units until it drops to 37.5 by 20 units. Okay, due to point load, and it remains constant between C and D. Remains constant at 37.5 between C and D. Now coming to B, the shear force at this point is minus 112.5 minus 112.5. So we take it downwards. Okay. So it varies from 37.5 plus 37 to minus 112. Okay. So at some point it changes sign. Let it be E, point E, where the shear force changes sign, and it is at a distance of 3.75 meters from B. The point E where the shear force changes sign is at a distance of 3.75 meters from B. So it is a positive shear force above the line and negative shear force below the line. This clear. So this is the shear force diagram for the given B. For the given B. Similarly, if you draw the bending moment diagram, bending moment at A and bending moment at B are 0. Being simple support, the bending moment will be 0. Okay, and between A and C, the bending moment varies linearly from 0 at A to a value of 115. Bending moment at C is 115. Okay. Similarly, this is at C, and at D, the bending moment is 227.5. Okay. At D, the bending moment is 227.5. 227.5. Now, there is a drop in the value of bending moment by 40 units because of couple. So it drops to 187.5. Okay. Say at point D only, the bending moment changes suddenly. Okay, because of couple. And how about the bending moment between D and B? It is parabolic. So 187 at D, 0 at B, and it varies parabolically. To draw a curve, we need one more point in between. Okay, and that point is E. At that point E, we have calculated the bending moment, which is maximum, and we got this maximum bending moment as 210.9, 210.95. Okay, so now you draw the curve joining these points. Draw the curve joining these points. So the maximum bending moment is at E, 3.75 from end B. So if you observe, the bending moment diagram throughout is positive. Bending moment throughout is positive. Okay. Generally, in case of simply supported beam, the bending moment diagram is positive, except in case where the couple is acting. Okay. Yeah. There is a possibility of negative bending moment also in case if the magnitude of couple is too large. Okay. Uh, there is a possibility. In all the other cases, that means without couple, in case of simply supported beam, the bending moment diagram will be positive. Okay. Yeah. Now let us see another example. Another example. Yeah, let us take an example of simply supported beam with a uniformly varying load. With uniformly varying load, varying from 0 at A to W at B. The intensity of loading varying from 0 at A to W per unit length at B. Okay. So how to draw the shear force and bending moment diagrams for this? Okay. Yeah, the procedure is the same in all the cases. First step is to calculate reactions. Okay. The reactions at A and B. Yeah, the procedure to find reactions is by applying equilibrium conditions. Sigma MA equal to 0. So what does this imply is RB into L, that is the anti-clockwise moment, that is equal to clockwise moment due to uniformly varying load. The load is uniformly varying. This is straight line variation, so it is uniformly varying. So the total load is W half into base into height. This is the triangular load. So the total load is given as uh, the area of the triangle, which is base L, height W by 2 into the distance of centroid. Where will be the distance of centroid? It lies at a distance of 2/3 of L from this end, because this end is the vertex, or 1/3 of L from B, because this end is base for the triangle. So from base it is 2/3 of L. From vertex it is from base it is 1/3 of L, and from vertex it is 2/3 of L. Okay. So here you take 2 by 3 L. So it gives RB. Okay. So here L cancels. So RB you will get WL by 3. WL by 3. And now by applying condition sigma V equal to 0, you will get RA. Okay, RA is equal to total downward load is the UVL, total load due to uniformly varying load, which is WL by 2, minus RB, which is WL by 3. So WL by 2 minus WL by 3, which is WL by 6. So the reaction at A is WL by 6. Okay. So before proceeding to draw shear force and bending moment diagrams, you need to first find the reactions at the supports. Okay, which are WL by 6 and WL by 3 at A and B respectively. So now we proceed to draw the shear force and bending moment diagrams. So here you need to consider section, and how many sections are required on it. It depends on the load, given given load condition. Okay, in this particular case, only one section is sufficient because only UVL is acting. So it is enough for us to consider one section between A and B at a distance x from A. And the intensity of load at this section is W dash, say, because the intensity at B is W per meter length. Let the intensity at the section x is W dash. How will you get the intensity at a distance x? By using similar triangle property. W dash by W, okay, W dash by W is equal to x by L. In similar triangles, the ratio of corresponding sides is equal. Ratios of corresponding sides are equal. If two triangles are similar, then the ratios of the corresponding sides. Corresponding sides means here W dash and W are the sides, corresponding sides. Okay. Similarly, X and L are corresponding sides. X is this length and L is this length. Okay. Here the triangles, this triangle and this triangle are similar. Okay. So the property of similar triangles is this: W dash by W equal to X by L. So from this, W dash is equal to Wx by L. Wx by L. Okay. Wx by. So knowing this, we now find the shear force at section X, shear force at section X. Considering left hand side here, what is the shear force at X? RA, that is WL by 6 minus the UVL acting to the left. Okay, this area of the triangle. So that is Wx by 2. W dash into x by 2. What is W dash? W dash is Wx by L. So shear force is WL by 6 minus Wx square by 2L. Replacing W dash by Wx by L, you will have Wx square by 2L. Now if you observe this equation for shear force, it varies as square of the distance. It means the variation of shear force is parabolic. The variation of shear force is parabolic. Okay? It is not linear. In case of uniformly varying load, the variation of shear force is parabolic. In case of UDL, uniformly distributed load, the shear force variation is linear. And in case of point loads, if there is no load acting between 2 points, 2 point loads, then the shear force remains constant between those 2 points. Okay, so that's how the shear force varies. Now, what are the limits for x? X varies from 0 to L. Okay, at x0, you will get shear force at A as WL by 6. This term becomes 0. Shear force at A is WL by 6. This is positive shear force. Left side upwards is positive. And at x equal to L, what is the shear force at B? So WL by 6 minus, replace L by x by L. So you will have WL square by 2L or WL by 2. Okay, WL by 6 minus WL by 2 is minus WL by 3, negative. So the shear force at B is negative because it is nothing but the reaction at B. It is nothing but the reaction at B. So it is right side acting upwards. So it is negative shear force at B. Okay. And one more thing is the shear force changing sign between A and B. What does this mean? At one section it becomes 0. It is changing sign means at the point where it changes sign, its value is 0. Okay. And to find the distance where the shear force is 0, we have to equate this to 0. So by equating that to 0, we will have Wx square by 2L is equal to WL by 6. Okay, which gives x square equal to W cancels L square by 3. X square is L square by 3 or x is L by root 3. So at a distance of L by root 3 from A, at a distance of L by root 3 from A, the shear force changes sign. And at this point, the bending moment is maximum. Okay. And how about the bending moment now? Bending moment at x. Bending moment at x is RA into x, WL by 6 into x minus WX square by 2L. What is that WX square by 2L? This term, WX square by 2L. The total load. Total UVL, uniformly varying triangular load. Okay, for a length of x into its centroidal distance from the section is x by 3. Okay, the centroidal distance from this point is x by 3. This is the base of the triangle. So the centroidal distance is 1/3 of x height. Okay, x by 3. So this becomes WL x by 6 minus WX cube by 6L. That is the bending moment at x. Okay. Now at x equal to 0, what is the bending moment? At A, 0. At x equal to L, what is the bending moment at B? WL square by 6 minus WL cube by 6L. That is WL square by 6 only. That is 0. The bending moment at B and bending moment at A are 0. Being simple supports, bending moments at A and B are 0. And how about the variation in between? It is cubic parabola. The variation of bending moment is cubic parabola. And we know that at x equal to L by 3, bending moment is L by root 3. Bending moment is maximum. Okay? And that maximum bending moment is given as WL by 6 into L by root 3 minus W by 6L into L cube by 3 root 3. Okay? L by root 3 to the power 3 is L cube by 3 root 3. So this is WL square by 6 root 3 minus WL square by 18 root 3. So multiplying and dividing with 3. So 3WL square by 18 root 3 minus WL square by 18 root 3. So it becomes 2WL square by 18 root 3 or WL square by 9 root 3. This is the maximum bending moment at the point where shear force changes sign. Okay. Now if you plot the diagram, shear force and bending moment diagrams for the beam with uniformly varying load. The shear force at A is positive, which is WL by 6, and shear force at B is negative, which is WL by 3. And the variation in between is parabolic. So how it changes? It varies something like this. Okay. This is the point C. Let it be C, where the shear force changes sign, which is at a distance of L by root 3. Okay. There is positive shear force and negative shear force, and this is parabolic variation, not straight line. Okay. And coming to bending moment, at B it is 0, at A it is 0, and at C it is maximum. Okay. And how about this value? W L square by 9 root 3. WL square by 9 root 3. That is the maximum bending moment. It is positive only. Okay. So this is the bending moment diagram, and this is shear force diagram. Okay. Yeah. So with this, I close this session. Thank you. We will work out some more examples in the next session.
Like, share and subscribe. Hit the bell icon for more updates.